Here is an example of a more difficult question involving emission spectra. It says calculate the frequency of the electronic transition from n equals 4 to n equals 1, where n1 equals 1 and n2 equals 4. As before, we can approach the problem in a series of steps. First, we identify what is asked for. We have to find frequency. Then we list the relevant information that is available to us. n1 equals 1 and n2 equals 4. Finally, we try to find an equation that will allow us to solve the problem. We have an equation for n1 and n2, but it does not contain the frequency, but we'll list it here anyway. We're familiar with this equation. 1 over lambda is equal to Rydberg's constant times 1 over n1 squared minus 1 over n2 squared. When faced with a situation in which the path to the answer is unclear, we can try to work backwards and meet somewhere in the middle. Since we have to find the frequency, we can list equations that contain frequency. So we have E equals h times nu, frequency, and frequency is equal to c over lambda. Since the second equation contains lambda, this suggests that this is the route to go. So now we only need to determine c, which is the speed of light, and equals 2.998 times 10 to the 8 meters per second. So now we simply solve for lambda as before, substituting in our values. So 1 over lambda, 1.097, over 1 squared, which is 1 over 1, minus 1 over 4 squared, which is 1 over 16. Evaluating the numbers in parentheses and multiplying by 1.097 times 10 to the minus 2, we get this. .0103 per nanometer. So lambda is equal to the reciprocal of that. Pay no attention to that little email that popped up. And we have a final answer of 97.1 nanometers. Now that we've found lambda, we can solve for frequency. However, one benefit of retaining the units throughout the calculation is that it reminds us that the wavelength is in nanometers. If we place it into our equation for frequency, we'll have a mismatch of units, since the speed of light is in meters per second. So we should change nanometers to meters using one nanometer equals 1 times 10 to the minus 9 meters. And so we can substitute in our value for nanometers and get this. Now we can solve. And we get frequency 2.998 97.1 times 10 to the minus 9 meters. The meters cancel, and so we're left with 3.09 times 10 to the 14 per second, or hertz.